is causation? There's a long tradition of thinking about causal relationships as a type of metaphysical glue holding things together. To use J.L. Mackey's evocative term, causation is the cement of the universe. Most analyses of causation focus on what it is that links cause and effect. But there's a different place we can begin. Instead of focusing on what links cause and effect, we can analyze the factors that prevent us from measuring causal relationships. Such factors are known as confounders. In these episodes, I analyze causation as the relationship that remains when you eliminate confounding. As a result, an account of confounding matters not just for the methodology of causation, but for understanding what causation is, and for distinguishing causal from non-causal relationships. Hello, and welcome to Causal Foundations. My name is Naftali Weinberger, and in this series, I introduce foundational concepts from causal inference in videos of approximately 10 minutes. Today's video will build on prior episodes. Although I'll review all the relevant concepts, you should watch episode 3 if you want the full picture. The concept of confounding I'll present here, which I'll refer to as the correct notion of confounding, contrasts with a more colloquial understanding of confounders as alternate explanations of an effect. Just so we have a concrete example of a disputed causal claim, consider Jonathan Haidt's recent book, The Anxious Generation, which attributes a decline in mental health to the use of smartphones. In criticizing his thesis, a natural thing to do would be to suggest alternative explanations for the decline in mental health. This type of example might lead one to think of confounders as alternate explanations of an observed outcome. Now, this way of talking is not entirely wrong, but today I'll argue that it encourages key misconceptions about causation. It makes it seem as if effects must be attributed to single causes, and further as if individual causes have unique context-independent effects. To give a precise notion of confounding, we need the graphical causal models that I cover in this series. The analysis of confounding brings together two ideas from episode 3. First, causal effects correspond to the results of interventions in the cause, which break all arrows going into it. The probability distribution of y resulting from an intervention on x is given by py given do x. This can differ from the observational distribution, the probability of y given x. A correlation in this distribution might merely indicate that the types of people who take a drug are more likely to recover, without indicating that the drug itself is effective. Second, identification concerns whether, given one's causal knowledge and a probability distribution, the magnitude of an effect is uniquely determined. In cases where there's an unmeasured common cause, the effect is not identified, since any correlation between x and y could be due to either the direct cause or the common cause, or both. The magic of identification is that it reveals what would happen were one to intervene without actually intervening. One way to identify an effect is using the backdoor criterion. Here I won't review the details, but in this simple model involving the effect of a drug on heart disease, gender satisfies the criterion. One can therefore identify the effect via backdoor adjustment. What this says is that the effect of x on y can be derived as a weighted average of the probabilities of heart disease given the drug in the male and female populations, weighted by the sizes of those populations. The probabilistic formula on the right-hand side identifies the causal effect. The path from identification to confounding is a short one. The conditions under which one can eliminate confounding just are those under which one can identify an effect. Variables that prevent one from doing so are confounders. Examples include common causes that one does not condition on, or common effects that one does, though the general analysis determines whether any arbitrary set of variables confounds a relationship. Confounders are said to bias an effect measurement. This means that when there's confounding, no matter how much data you collect, you in principle cannot identify the effect. Identification is not the same thing as estimation, which concerns the statistical methods for measuring an effect from data. Identification is about whether one can in principle measure an effect. We can already begin to see how the more precise notion of confounding differs from the colloquial one. Note that what is confounded is a causal effect, which is here understood as a relationship between variables. In defining confounding, we do not assume that a variable takes on a particular value, and in particular not that an outcome occurred. So the question of how to explain an observed outcome is a different one from confounding. While common causes confound a relationship, independent causes don't. Suppose that in the drug example, gender did not influence who took the drug. It still could be the case that one's chance of heart disease differs depending on whether one's male or female. This is called effect heterogeneity. Heterogeneity by itself does not produce confounding. When gender isn't a common cause, one does not need to condition on it in order to get an unbiased effect measurement. In this expression, the first line says that the observational distribution, the probability of y given x, identifies the effect in the population, and the second says that this is just a weighted average of the effects in the subpopulations. For instance, if the drug lowers the probability of heart disease by 20% in men and 10% in women, and the population is 55% women, then the average effect would be to reduce the chance of heart disease by 14.5%. While knowing gender would allow us to get a more precise effect, this result is the correct average effect for a randomly sampled person from the population. Now that we have the correct understanding of confounding, let's contrast it with the more colloquial one. Why am I so critical of talking about confounders as alternate explanations of an observed effect? First, this way of talking suggests that the existence of multiple causes is itself problematic, but independent causes of an effect are not confounders. Relatedly, it might lead you to think of causes as having determinate, context-independent effects, and to think of heterogeneity as hindering identification. But heterogeneity by itself does not produce confounding. Finally, it makes it sound like the basic causal question is that of what brought about the occurrence of an effect that is known to have occurred. Such questions are studied under the name of actual causation. But confounding is not about actual causation. It's about learning the relationship between the cause and effect variables without assuming anything about which values are instantiated. So where does this all leave us with the question of whether the mental health crisis is due to iPhones? Or really any question where we want to learn about why a particular effect occurred? The point of today's episode is that these types of questions are not the direct target of an account of confounding. Confounding concerns whether a relationship between variables is genuinely causal, rather than which factors explain a particular outcome. Of course, if there were no general causal relationship between iPhones and depression, it would follow that iPhones are not responsible for a particular rise in depression. But before we can address the more specific question, we need to know whether there's a more general causal relationship. And it is this question which is addressed by the general analysis of confounding. Thank you for listening. For further reading, check out Felix Elwer's chapter on graphical causal models. And if you made it this far, please don't forget to like and subscribe.